So here the next part of the discussion is, that is, in the isomerism, let us go to structural isomerism. In structural isomerism, we'll go with the first one, that is ionization isomerism. Here the first point what we have to understand is between pair of complexes, exchange of ligands with respect to primary and secondary valencies. Occurs, and you find that because of this there is a color change. You find that there is a color change observed in complexes. There is a color change which is observed in the complexes. The coordination number remains constant for the metal complex, and the metals also in the complex, they remains constant. So for example, if I am taking platinum of NH3 taken 5 times of Cl2 of Br2, and platinum of NH3 taken 4 times, taken 4 times of Br2 of Cl2. If I take, in both the cases you are finding that there is an exchange of ligands taking place between the chlorine and bromine, but the coordination number of the platinum is remaining constant here. And suppose here if I am adding silver nitrate, then I am going to get silver bromide as the precipitate, 2 moles of silver bromide precipitate, which is yellow in color. And here if I take, this is the first example, if I am going to add silver nitrate here, and you are going to get 2 moles of silver chloride, which is a white precipitate. So that means you are able to find the color change, and you are also able to find the interchange of the valences, primary valences to secondary valences and secondary valences to primary valences. So if you want, I can give you one more example. That is, for example, in the example 2, you can take same example. You can take platinum of NH3 taken 5 times of Br of chloro group. This solution in the aqueous state, it is red color solution, and in the next case again you exchange the valencies here. So you find the platinum of NH3, so taken 5 times of, that is chloro group, and here the bromo group, and here this is a violet color solution, violet color complex. This is a violet color complex, and this is red color complex. That is because here the Cl minus ion is going to give red color, and the Br minus ion is going to give, that is violet color complex. So this is the end of the ionizational isomerism. Now let us go for the next case, second one, that is linkage isomerism. Linkage isomerism is due to the ambidentate nature of ligand. What do you mean by ambidentate nature? If there is a ligand and if it contains a group, that group contains 2 different sites, X and Y. X and Y are the 2 different sites for coordinating with metal in complex to satisfy coordination number, its coordination number. This is the ambidentate nature of the ligand. So for example, if you are taking NO2, already I have explained this. If If you go for NO2, it has two different sites. One is one NO2 group, you can just take metal of coordinate covalent bond. It has double bond and it is coordinate covalent bond. So this is the sharing. That means here the nitrogen is trying to donate a coordinate covalent bond for the metal, and in the next case metal which coordinates with the oxygen, underline oxygen, and you find the single bond nitrogen, double bond oxygen. So here you find that oxygen is trying to coordinate with the metal, oxygen is trying to coordinate with the metal in the case of nitro group, and in the first case nitrogen is trying to donate with the coordinate with the metal in the first group. So there are two different cases here. Here nitrogen is X, and oxygen is Y. So two different sites, X and Y. So this is the main nature of the ambient nature of the ligand, and that comes to linkage isomerism. So here take one example of the linkage isomerism. Take an example of linkage isomerism. That is, you can take cobalt of NO2 of NH3 taken 5 times. I'm underlining this. Here nitrogen is going to coordinate with the cobalt here in this complex. So therefore here this is going to become, this is yellow color complex, and in the next case, and you can just add one more, cobalt of ONO coordinating complex with NH3 taken 5 times. So here this is going to become a red color complex. So now this is very clear that in both the cases, here nitrogen is trying to coordinate with the cobalt, and here oxygen is trying to coordinate with the cobalt. So two different atoms are coming in coordination with the central metal. That's why this is a perfect example of the linkage isomerism. So here the third category of the structural isomerism is, third one is, that is hydrate isomerism. Hydrate isomerism, it is a special type of ionization isomerism. It is a special type of ionization isomerism. This hydrate isomerism arises because of the presence of H2O molecules inside and outside the coordination sphere, inside and outside the coordination sphere. Suppose for example, if I am taking chromium of Cl3 of 6 molecules of H2O, then this we can convert into Werner structures. That is, you can take chromium of H2O taken 6 times of Cl3. So this is, here you get violet green color. The next case, bring one water molecule outside and take chloro group inside. So chromium of H2O taken 5 times of chlorine of Cl2 of H2O. This is light green color. This is light green color, and here next case you try to bring one more water molecule outside. So chromium of H2O taken 4 times of, bring one more chlorine inside, 1 chlorine and 2 H2O. This is dark green color, and the last one is, if you are bringing all the 3 chlorines inside, then chromium of H2O taken 3 times of 3 chlorines of 3 hydrate, then this is going to become colorless complex. So what you are noticing here is, you are finding that there is an adjustment of the water molecules as ligands within the coordination sphere and outside the coordination sphere. In the first complex, we have all the 3 chloro groups outside the coordination sphere acting as primary valencies. So therefore 3 three Cl minus ions are going to give violet green color. In the next case, you are bringing one primary valency inside, so it plays the role of dual valency. The chloro group plays the dual valency. If it is dual valency, yes, the color also will change. 2 Cl minus ions are going to give the light green color, and if you bring next 2 chlorines inside, dark green color. In the next case, you find that all the 3 primary valencies have been brought inside to satisfy the coordination number of chromium. That's why outside there is no primary valency. That's why you cannot ionize this complex, so its conductivity is 0. So therefore finally the complex becomes colorless solution. So the next part of the isomerism is, that is coordinational isomerism. The next part is coordinational isomerism. In the coordinational isomerism, what we are noticing here is, the first important point what you have not noticed is, this coordinational isomerism always occurs between pair of complexes, that is between cationic and anionic complexes. Cationic and anionic complexes. What is the principle involved in the coordinational isomerism? Mutual exchange. This is mutual exchange of ligands between cationic and anionic complexes. Mutual exchange of ligands between cationic and anionic complexes results in the formation of coordinational isomerism. One thing what we need to understand here is, in the case of coordinational isomerism is, that is you can select any coordinational isomerism. For example, if I am taking chromium of NH3 taken 6 times of 3 plus, and here I am going to take cobalt of cyanide taken 6 times of 3 minus. So remember that whenever the complex is having a neutral ligand, whenever the given ionic complex is having a neutral ligand, then that overall complex is going to become cationic. Whenever it is having a negative ligand, you find that the overall complex is going to become anionic complex. So here we have anionic ligand, so the complex is negative. Here it is cationic ligand, so the complex is positive. So positive, cationic, negative, anionic complex. So exchange of ligands taking place between the two charged complexes, that is cationic ligands and anionic ligands. Exchanges occurs, then such mutual exchange of ligands taking place between the cationic and anionic complexes results in the coordinational isomerism. The coordinational isomerism means, to retain both the metals in the cationic and anionic complexes, they try to retain their coordination number fixed, and they try to retain the overall secondary valence also intact. Only thing is that just their number of ligands keeps on moving from one part of the complex to the other part of the complex, and the stability of the complex is also retained as such. So what is happening here? So now suppose if exchange is taking place, and I am going to take it like this, and if I am taking chromium of NH3, bring one cyanide here. So this is 5 and this is Cn. I'll bring one cyanide here. Now the charge is going to become 2 plus, and here cobalt of cyanide taken 5 times, and bring one ammonia over here. So therefore you find that here it is 2 minus, and you can continue. And if I am going to bring 2 cyanides from there, keeping only 4 ammonia molecules, you find that here it develops only one positive charge, and here it develops, that is Cn taken 4 times of NH3 taken twice, so it develops only one positive charge. And you can write, and here chromium of NH3 taken 3 times and cyanide taken 3 times, then here also you find that cobalt of cyanide taken 3 times and NH3 taken 3 times. Neither of the complex will try to acquire positive charge. So you are finding that there is a continuous exchange of ligands taking place between the cationic complex as well as the anionic complex, and that will result in the mutual exchange of the ligand between cationic and anionic complexes, and that will result in the coordinational isomerism. So here if you go to the next part, second part of the discussion, that is you go for stereoisomerism. Stereoisomerism, it is made up of the geometrical isomerism. So in this geometrical isomerism, let me give you the generalization. What are the conditions? Actually, if you take metal complexes, all the metal complexes, we can go like this. If you go for metal complexes, if you're going for the metal complexes, Ma2B2 complex will give geometrical isomerism, and its coordination number is 4, and it can be square planar. It can be square planar or sometimes even tetrahedral. If it is tetrahedral, then you can take, that is, if it is tetrahedral, then you can take that is Ma2B2. Here also the complex is Ma2B2 only. Again, you can also take Ma2BC, also can give geometrical isomerism. Its coordination number is 4. Yes, it can be square planar or sometimes it can be tetrahedral, and it is almost the same condition. Very rarely you can also find all the metal complexes with the MABCD also can give geometrical isomerism, and coordination number is 4, and it can be tetrahedral. And we cannot differentiate this MABCD, we cannot differentiate this into, that is the cis and transform, but we can get 2 or 3 different isomers. But in the case of Ma2B2 or Ma2BC, we can get 2 isomers, one is cis and one is trans. In both these cases, we can get one cis form and we can get one trans form. So that means you can get 2 isomers. You can get 2 isomers here. Likewise, if you go for Ma2B4, we can take, yes, it will give geometrical isomerism. Its coordination number is 6. If its coordination number is 6, it is octahedral. If it is octahedral, then its hybridization is sp3d2 or d2sp3 hybridization it can show. Sometimes you can also take Ma3B3, also it can give the geometrical isomerism whose coordination number is 6. Again, it is octahedral. But it has, yes, it is definitely, it lies in the octahedral plane, but it has facial and meridional. It has 2 cases, facial and meridional. Yes, in the case of Ma2B4 and Ma3B3, we can get again cis and we can also get trans isomers in both these cases. In this we can get facial and meridional, and also we can get cis and trans cases, and the hybridization is sp3d2 hybridization. So these are some of the generalizations which we can make. And here M stands for, so here M stands for, M is the central metal of the complex, and here that is A, B, C, D, sometimes even EF also. Okay, all these are ligands attached. All these are the ligands which are attached to the central metal in the complexes. So basing on this, now we are going to work out one by one different kind of examples, and we are going to prove how we can get the cis and trans isomers in the case of different metal complexes with coordination number 4 and coordination number 6. So here now let us go to the first case 1. If we take, that is Ma2B2 complex, example platinum of NH3 taken twice of Cl2 So if you take this complex, it is in the form of square planar symmetry. So it is in the form of square planar symmetry. So what I can do here is, like, I am going to take the complex like this, take the platinum central metal, and here you can take, that is, here you take one ammonia, and here also you take one ammonia, and here you take one chloro group, and here you take one chloro group. So this I can say cis. If I take this as cis, or else you can just place it, you can place one ammonia over here, and here you can place one chloro group over here. So I can say that this is in the cis form. This is in the cis form. So now try to interchange the same complex. You can interchange. Actually here there is no bond, so what I am going to do is, I am going to show a dotted line like this. Here also there is no bond, so take a dotted line like this. Here also there is no bond, so take a dotted line like this. Here also there is no bond, so therefore take a dotted line. So this is in the square planar symmetry, this form of square planar symmetry complex. So here I can take, this is the complex. In the next case, you can take again platinum. So here you try to take, flip one of the nitrogen, take the ammonia molecule over here, and you bring the chlorine over here, and here take one chlorine and bring the ammonia molecule. So this is going to become definitely a trans case. Trans case, this is transform. Dichlorodimine platinum complex. Dichlorodimine platinum complex. This is cis form of dichlorodimine platinum 2 complex. So same thing applies here also. And this is how we can prove, that is Me2B2. Now suppose for example, if I am taking case 2 in the geometrical isomerism, in the case of case 2 of geometrical isomerism, now if I take Ma2B4, if I am going to take cobalt of NH3 taken 4 times of Cl2, if you take, then I think we can take this complex, because it is octahedral complex, its coordination number is 6. So directly what I need to do here is take one complex like this, one octahedral complex, take the cobalt in the center, and take one bond like this and one bond like this. And the best thing what we can do here is, like, we can place all the 4 chloro groups, 4 ammonia molecules. One ammonia molecule I am placing over here, and one ammonia molecule I am placing over here, and another ammonia molecule I am placing over here, and another ammonia molecule I am placing over here. So this is in the octahedral form of octahedral complex. So I can say all cis. So this is here cis to cis. There was a small changes being done in order to accommodate the cis structure for this complex. So you can see that both the ammonia molecules, they are adjacent here. Here also both the ammonia molecules are adjacent. Cis of cis, cis of cis, 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 and both the chlorines also, they are at the adjacent. So I can say all cis, all cis. Now you can convert this in the next structure. If I am going to take cobalt in the center and exchange these two cases, if you are going to exchange both these cases, you are going to find that here keep the ammonia molecules like this only. Here also keep the ammonia molecule like this, and bring the ammonia here, and here you keep the ammonia like this, and you can take both the chlorines over here. So you can find that here, that is, these two are cis, this is also cis, but you can see that these two cases are trans. The chlorine and above the plane and below the plane is going to become trans, that is cis comma cis comma trans. And here you can say, when I say all cis, you can say cis comma cis comma cis, but this is cis comma trans. So therefore overall it is cis, and here overall it is trans. So therefore we can just convert the cis form of isomer to the trans form of the isomer in the structural isomerism, and it is an octahedral complex. In both the cases it is octahedral complex because it has the octahedral geometry like this. This is the octahedral geometry. Here also this is the octahedral geometry in both these cases. This is the octahedral geometry. So if you go to the stereoisomerism, in the stereoisomerism, the last part of the discussion, that is the case 3. In case 3, let us take, that is A3 of B3 isomers, and here example you can take cobalt of NH3 taken thrice of Cl3. If you are going to take, then this is going to be shown in the form of, that is, take the complex here, metal complex, take the cobalt, here you take one case like this. So take 3 ammonia molecules back to back at the 3 corners like this, at the 3 corners, and take 3 chloro groups also in the same pattern. So you are finding that here this isomer, right now this isomer, I can say it's meridional, because you can see that it is just cutting across the meridian like this. This is the meridian. Here also, if you join it, then you can see that if you're going to join it, yeah, you can just cut it like this. These are the meridians, meridional, and next if you go for the facial, again take the cobalt and exchange one of the ligand over here, bring the ammonia group and chloro group interchange. So take the ammonia molecule over here and take the ammonia molecule over here, then again bring the one more ammonia molecule over here and chlorine over here, and this is one more chlorine, and you can find that here the 2 chlorines, yes, the 2 chlorines we can just, yeah, the other 2, that means the interchange is taking place between this ligand and this ligand. The rest of the positions are remaining intact. If you select the facial, so what we are noticing here is, I think this is the shaded region between the 3 ammonia molecules. This is the facial pattern. So here this is facial, isomer, and the meridional, and this is facial. So you can see that these 3 ammonia molecules are within the internal plane of the square planar structure, and so we can take this as the facial isomer. So Ma3B3 is going to give definitely facial isomer. Now we will go for the next part of the discussion, that is case 4. In case 4 of stereoisomerism, yes, we will go for optical isomerism. In the optical isomerism, it's a part of optical isomerism. I can go like this: optical isomerism in metal complexes, in complex compounds, is a part of geometrical isomerism. It's a part of geometrical isomerism. First point. Second point, only the cis form of geometrical isomerism, GI stands for geometrical isomerism, only the cis form of geometrical isomerism gives the optical isomerism. And cis and trans form of geometrical isomers are called diastereomers. At least one bidentate ligand in complex or in complexes is prerequisite. Bidentate ligand in the given complexes is a prerequisite. So if that is the case, I just want to continue over here. We have some space, so here I can take, that is CO ethylene diamine taken thrice of 3 plus can give the optical isomerism in the form of that is dextro and levo. It will give cis, and trans, it gives cis and trans, but only cis will give you the optical isomerism. Then you can also take, that is chromium of OX taken twice of 3 minus also can give the optical isomerism, but this is the cationic complex and this is the anionic complex, and in both these we can obtain the optical isomerism from cis, and cis and trans are going to become the geometrical isomers. So here if you go to the optical isomerism, as already we have discussed, optical isomerism in metal complexes, again I am repeating the same examples, that is I can take cobalt of ethylene diamine taken thrice of 3 plus comma, that is you can take cobalt of oxalate trioxalate of 3 minus comma, platinum of ethylene diamine taken twice of Cl2 of 2 plus, and so on. But in these three examples, what you are noticing is, in all these three cases you are finding that definitely there is a bidentate ligand. For example, if you take En is nothing but ethylene diamine, it's a bidentate ligand, ethylene diamine is a bidentate ligand, and so therefore you can take, it's a bidentate neutral ligand, and you can take here OX, if you take OX2 minus is nothing but oxalato bidentate, it's a bidentate ligand. If you want, I am going to give you the structures of oxalato also, that is, this is the structure of oxalato with the 2 lone pair of electrons, this is oxalato, and ethylene diamine you can take CH2 single bond, CH2 NH2 with a lone pair of electron. Yes, here also NH2, if you take NH2 with a lone pair of electron, yes, it's a bidentate ligand. So now for example, if I am going with A, going with B and going with C, if one or two examples if you are going to try, then it is automatically it's going to become easy. Definitely this is an octahedral complex. Here the coordination number of cobalt is 6, so it should be definitely octahedral. Here also the coordination number of cobalt is 6, so definitely it should be octahedral. Here also the coordination number of platinum should be 6, so definitely it should be octahedral. So go with respect to A, so directly I am taking here, that is take the cobalt, and here you mark one ethylene diamine molecule, here you mark one ethylene diamine molecule, and here you mark one ethylene diamine molecule. So here I can take it like this, this is one coordinate covalent bond, then here I can take, this is one more coordinate covalent bond, and this is another one which I want to take coordinate covalent bond, and this is going to become 3 plus. I can say that this is definitely the cis form of geometrical isomer, tris ethylene diamine cobalt 3 complex. This is actually, and it is cis form. You place a mirror. When you are going to place a mirror over here, you find that there is an interchange taking place. So what I am observing here is, take the complex again, take the cobalt complex, and you reverse this, rotate all the ligands through an angle of 180 degrees. So you find that here you can take one ethylene diamine molecule here, and here you can take one more ethylene diamine molecule over here. So here you can take, that is, okay, I am taking it in the center. So this is one case where you can create, and here also I am going to take one more ethylene diamine, wherein which I can take. So that means there is a rotation. You can see that there is a difference in the rotation of the plane polarized light. I mean, the ligands are trying to change their position at the rate of 180 degrees. You can see here the ethylene diamine here in the square planar plane, one ethylene diamine bidentate ligand is in the left side, and here the same ethylene diamine bidentate ligand is on the right side, and the rest of the two are outside the square planar, that is octahedral plane. The rest of the two bidentate ligands are in the octahedral plane, so therefore they are in the right side of the plane, but after facing the mirror they have come to left side. So I can say that these two pairs are going to become, that is cis of, I can say cis of dextroform, cis of D of plus, and this is cis of D, cis form of L of minus, minus sign. So both these can become enantiomeric pair, and they can become, that is racemic, and finally they can become optically active. So in this way we can prove the optical isomerism in the rest of the two cases also. For example, if I am taking platinum case, go for the C bit. If I am going with the C bit also, I can do the same thing here. Take the platinum over here, then take the ethylene diamine molecule, one ethylene diamine molecule I am taking over here, another ethylene diamine molecule I am taking over here. So this is what I want to take. Here. Okay. Then here I am taking the ethylene diamine molecule over here. So this is what I would like to take. And in the rest of the two cases, here I am going to place one chlorine, and here I am going to place one more chlorine, and this is all cis. So place a mirror. Again you find that after the rotation has been taking place, again take the platinum, you can definitely see that ethylene diamine comes to the left side. Now here it is right side, now it has come to left side. Now here it is on the left side, so take it to the right side. So you can just take it like this, and here we have chloro group. Take one chloro group here and take one chloro group over here, and this you can find that, yes, you can find that this is cis of D form, and this is cis of L form. So therefore these two have become the pair of enantiomeric mixtures. They are enantiomeric pair, they become racemic, and they become optically active. And it is very clear that definitely whenever the bidentate ligand is there in a given complex, definitely it is going to show optical isomerism. The next part of the discussion here is, VB theory of metal complexes. VB theory of metal complexes. Here VB stands for, VB means valence bond theory. Valence bond theory. In the valence bond theory, if you take in this valence bond theory, you take a metal complex. If you take a metal complex is made up of a metal plus ligands. Metal ligands always coordinate. Ligands always coordinate with metal to satisfy the coordination number. In the meantime, what is happening here is, if in the aqueous solutions, every metal complex in aqueous solution, it ionizes in such a way that approach of ligands to central metal is ionic, and if the approach of ligands around the metal, if it has uniform plane of symmetry, then the degeneracy of the d orbitals, that means these metals, that means metal contains d orbitals, and these d orbitals are always degenerate. When they degenerate, all the orbitals they contain, they remain intact like this. 1, 2, 3, 4, 5. They remain intact like this. That is this is dz square dx square minus y square dzx dx y and dyz. All these are degenerate. When the ligands have uniform plane of symmetry, that means the attacking of ligands, when they have uniform plane of symmetry, these d orbitals, they do not split, they remain intact. All the d orbitals of the d sublevel, it remains intact. But once the attack of ligands is not, the uniform plane of symmetry is not acquired by the attack of ligands on the metal, then the degeneracy is lost. So once the degeneracy is lost, so you can just take it like this: 1, 2, 3, 4, 5. These are the d orbitals. D orbitals. Then here these d orbitals, they split into two parts. One is they are going to split in the form of duplets and another in the form of triplets. So here I can take d, this is dx square minus y square, and this is dz square, because these ligands, they go along the axis of the attack of the ligand, so they experience more repulsion, that is why they acquire more energy. And here this is dxy and this is dyz and this is dzx. So because these are totally 5 orbitals, that's why the ratio is distributed in such a way. And this, because they are splitting, so the splitting is given by delta. Here delta means, delta represents, I can add one more point here, delta is nothing but crystal field splitting crystal field splitting factor. So if it is crystal field splitting factor, and if the complex is octahedral complex, then I can just mark this as delta naught. It is also called as Barry's center. So here what is happening, here there are 2 orbitals and here there are 3 orbitals. So here you find that because these orbitals, they have these are duplets and these are triplets, that's why this is given by E of G and this is given by T of 2G. They are designated by T of 2G, triple degenerate and double degenerate. So because of this, what is happening, I repeat, because of this, you find that out of 5, here the ratio for this double degenerate Eg for double degenerate, we can take it as 3 by 5, and this I'll take it as 2 by 5. So 2 by 5 is 0.4 and here 3 by 5 is 0.6. That means you find that there is an increased energy equivalent to 0.6 for Eg. That means for Eg set of orbitals delta naught is equal to 0.6, and for T of 2G factor 2G set of orbitals, you find that delta naught is equal to 0.4. So that's why now what is happening, because of this, it all depends upon this kind of splitting, again depends upon the nature of ligands. The splitting of the orbitals, the splitting of d orbitals in the metal complex, again depends upon nature of ligands. When you go for nature of ligands, these ligands are of 2 types. One is strong field ligands, SFL, another one is weak field ligands. SFL is called strong field ligands and WFL is called weak field ligands. So these strong field ligands and weak field ligands, they try to show a lot of influence on the splitting of the orbitals and acquirement of the delta naught value for both the set of orbitals. So therefore, from this, now we will go for the classification of strong field ligands and weak field ligands, and we will try to study the different cases of the complex compounds and their geometry and their hybridization. So here, if we go for the classification of strength of ligands, if we take, so I'll take that is, in the classification of strength of ligands, I am going to take weak field ligands and strong field ligands. So first of all, I would like to highlight the weak field ligands. If I go for WFL, weak field ligands, strong field ligands. So that means WFL stands for weak field ligands. Weak field ligands, and SFL stands for strong field. SFL stands for strong field ligands. So in the case of weak field ligands, we can take that for all the weak field ligands, delta naught is delta naught value, you can take it is less than P. This is because here P is the average pairing energy. Average pairing energy. Here in the case of strong field ligands, delta naught, crystal field stabilization energy. Delta naught is the crystal field stabilization energy for the octahedral complexes, which is greater than P. So this is again P is equal to average pairing of energy. Average pairing energy. So this also means that always weak field ligands, they are high spin complexes. All weak field ligands, they are high spin complexes. They form high spin complexes. Then here strong field ligands, they form low spin complexes. They form low spin complexes because they violate Hund, Aufbau's and Pauli's exclusion principle. Pauli's exclusion principle. That's why we can say that they form low spin complexes, strong field complexes. So here in the case of this is high spin complexes because they obey, I can say that since they obey Hund, Aufbau's and Pauli's exclusion principle. Pauli's exclusion principle. Also, you can say that because all weak field ligands, because the ligands are weak fields, then I can say that they always gives rise to complexes. They give outer orbital complexes. They always give outer orbital. They always give outer orbital complexes, and here they give inner orbital complexes. Inner orbital complexes. That's why we can say that in the case of weak field ligands, because they are giving outer orbital complexes, they form the hybridization octahedral complex sp3d2. They give the hybridization of the type sp3d2 octahedral, sp3d2 octahedral, sp3d2 octahedral, sp2d square planar type of complexes, and usually they are paramagnetic. I can say that they are paramagnetic because they have more number of unpaired electrons. But if you go for the strong field ligands, yes, they give D2sp3 octahedral complexes, D2sp3 octahedral complexes they give, then dsp2 type of square planar complexes they give, and usually they are diamagnetic. So what are the examples you can give? Examples of weak field ligands. Examples of weak field ligands you can take, that is F minus is a weak field ligand, then you can take Cl minus is a weak field ligand, then oxalato is also a weak field ligand. All these are weak field ligands. If you go for examples of strong field ligands, if you take, yes, you can take, that is number of examples you can take. CO, carbonyl group, is a strong field ligand. Then you can take ammonia, is a strong field ligand. Then you can take that is Cyanide is a strong field ligand. Cyanide is a strong field ligand. Water is a strong field ligand. So on and so forth. All these are the examples of strong field ligands and the weak field ligands. So usually, so here what we are noticing here is that is so now we have to select those complexes which are under the category of weak field ligands, and we have to select those complexes which are under the strong field ligands. So here in the case of weak field ligands, then the distribution of electrons, distribution of electrons in complexes with the weak field ligands. If you take that is, suppose if I am taking 3 set of orbitals and 2 set of orbitals, total 10 electrons you are supposed to fill up, then you can take it like this: 1 2 3 4 and 5. Then 1 is paired with 6, 2 is paired with 7, and 3 is paired with 8, 4 is paired with 9, and 5 is paired with 10. That means first electron, first, second, third, fourth, fifth, sixth, all becomes unpaired first, then the pairing will start. So this is how the distribution takes place in the case of weak field ligands. Now if you go for strong field ligands, distribution of electrons in the case of distribution of electrons in complexes with the strong field ligand. So here the distribution goes like this. First you take the 3 cases and 2 cases double degenerate, T of 2G and D of G. Then you can see that 1 2 3 4 5 6 7 8 9 and 10. That means they are not trying to obey the Hund's rule and the Abbas principle. That's why you can see that the pairing takes place in this pattern. So now it is very clear that there is a lot of difference in the distribution of electrons for the weak field ligands as well as the strong field ligands in a given complexes. So here take one question here. Analyze the given complexes. Analyze the given complexes with their geometry, hybridization, then structure and their magnetic nature. This is the question. So first one I am giving you NiCl taken 4 times of 2 minus, first one. Second I am taking NiCN taken 4 times of 2 minus. Third one I am giving you nickel tetracarbonyl. Fourth one NiNH3 taken 6 times of 3 plus, and the last one that is COF6 of 3 minus. So let us study in all these cases. Let us study one by one. If I take nickel tetrachloro nickel to nickelate 2 complex, it's an anionic complex. Nomenclature, this is tetrachloro nickelate 2 complex this is. So how do you calculate the oxidation state? Oxidation state of nickel is +2. If the oxidation state of nickel is +2, take the nickel, 28 is the atomic number, it is carrying +2 oxidation state. Write the configuration. So argon of 4s2 3d8 is the configuration, but it is carrying 2 units of positive charge, so I am removing 2 electrons. 4s0 3d8. If it is 4s0 3d8, then because chloro group is, and here one more thing what we have to understand here is the chloro group, the chloro is a weak field ligand. If it is weak field ligand, it forms outer orbital complex. If it is forming outer orbital complex, then let us see what is happening. If it is forming outer orbital complex according to the VB theory, it will utilize NS, NP and Nd orbitals for the hybridization. So therefore what we can do here is, like, come on, let us take the nickel configuration, because it is utilizing the NS, NP and Nd configuration. So that is, I am just going to take again the configuration as nickel 28 of +2. I am going to take it as 3D8 of 4s0 of 4p0. I am going to take standby. So if you take 3D sublevel, it has 5 orbitals, 1 2 3 4 5. So 1 2 3 4 5 6 7 and 8. So because chloro group is a weak field ligand, so it cannot forcibly violate the Hund's rule of or Aufbau's principle, and it cannot convert the two unpaired electrons to paired electrons. So it is not going to violate the Hund's rule or Aufbau's principle or Pauli's exclusion principle. It's not going to violate. It is obeying all the rules of writing the electronic configuration in the given orbitals, and the ligand is a weak field ligand. That's why this weak field ligand is not going to disturb the two unpaired electrons which are present in the 3D orbital, that is n-1 of d orbital. That's why it is going to search for the next level of the orbitals, next set of orbitals of the same energy level, that is 4s and 4p. So therefore 4s orbital has one vacant orbital and 4p has 3 vacant orbitals. Number of ligands present in the tetrachloronickelate complexes, there are 4 ligands, so there are 4 vacant orbitals. So therefore it is going to form 4 coordinate covalent bonds like this, and definitely this is s orbital and this is px and this is py and this is pz. So therefore it will undergo sp3 hybridization, and because it is undergoing sp3 hybridization, the structure of the nickel tetrachloride complex is going to become Ni of chlorine group, chlorine, chlorine and chlorine. So this is going to become the tetrahedral complex like this. You can take the 2 negative charges, it is tetrahedral. This tetrahedral complex, it is undergoing sp3 hybridization. It contains 2 unpaired electrons in the 3D orbital. This is 3D orbital, it contains 2 unpaired electrons. So that means number of unpaired electrons are 2. So therefore it is paramagnetic. It is paramagnetic complex, and the Bose magneton also you can calculate, that is mu is equal to under root of n of n plus 2 of Bose magneton. So substitute the values. So mu is equal to under root of 2 of 2 plus 2. So this is going to become root 8. Root 8 means 2 root 2. So 2 root 2 means 2.828. Bose magneton is the answer for the magnetic moment. So this is the complete information we are trying to gather for the tetrachloronickelate complex. So likewise we have to now do it for tetracyanonickelate complex. So the first one is completed. Now we are going for the second one. We'll go for the second one, that is d-bit nickel tetracyanoanionic complex. So nomenclature, this is tetracyanonickelate 2 complex is the IUPAC nomenclature. Here cyanide is a strong field ligand, so therefore it is going to form inner orbital complex. If it is going to form inner orbital complex, that means it is violating the Hund's rule, Aufbau's principle and Pauli's exclusion principle. So that's why standby, first you take the nickel oxidation state, which is going to become +2. So +2 oxidation state, 28 atomic number, organ of 4s2 3d8. It is having +2 oxidation state. So you remove 2 electrons here, because it is forming inner orbital complex according to VB theory. According to the VB theory, it utilizes n-1 of d orbitals, ns orbital and np orbital. So therefore I am going to rearrange the configuration. Organ of, that is 3d8 4s 3d8 of 4s 0 of 4p 0. So therefore this is going to become, that is, now take the configuration. 3d8 means that is 1 2 3 4 5, again 4s of 4p. So here in the case of 3d8, 1 2 3 4 5 6 7 8. Yes, so what is happening here is, because cyanide is a strong field ligand, so it will, cyanide being a strong field ligand, it will forcibly violate the Hund's rule and Aufbau's principle, and it is going to pair this electron. This is 3D actually this is 3d8, this is 4s0, and this is 4p0. So again, after pairing, the new structure looks like this: 1 2 3 4 5. So 1 2 3, 1 2 3 4 5 6 7 and 8. So this pairing is done here. So you're finding one vacant orbital here, and you also find, so that means because there are four cyanide ligands are there, so one cyanide it is going to utilize the 3d orbital. So then one cyanide from 3d orbital, one vacant orbital from 4s, and another two vacant orbitals from 4p. So therefore here pairing is going to done, donation is going to done, donation is going to done, donation is going to done. So therefore here we can take this as DsP2 hybridization takes place in the case of tetracyanonickelate complex. So DsP2 hybridization means, so therefore now we can come to the conclusion: hybridization is equal to DsP2 inner orbital complex. DsP2 means it is square planar. It is square planar. If it is square planar, then the structure can be look like this. Take four cyanides like this. Here attach one cyanide, here attach one cyanide, here also you attach one cyanide, here also you attach one cyanide. Take the complex. This is 2 minus. This is square planar. And here you are finding that there are no unpaired electrons at all. No unpaired electrons at all. So that is n value is 0. So no unpaired. So it is diamagnetic. If it is diamagnetic, then mu magnetic moment is also equal to 0. So this is something about the second case, tetracyanonickelate. So if you go to the third case, go for the third case, that is nickel CO taken 4 times. Actually it is a metal carbonyl. It's a metal carbonyl complex. It's a neutral complex. It's a neutral complex. So therefore the oxidation state of nickel is 0. If the oxidation state of nickel is 0, and here carbonyl is a strong field ligand, flexidentate ligand, and definitely it is going to form, let us assume that it is definitely going to form inner orbital complex. If it is forming inner orbital complex, let us see what is happening. Let us see, because directly without making an analysis we cannot outright say that it is going to become a metal complex. So that's why what we are going to do is take the nickel, atomic number of nickel is 28, oxidation state is 0, so mark it as 0. So therefore argon of 4s2 3d8, but because it is a strong field ligand, it utilizes n-1 of ns, np combination of orbitals. That's why we need to rearrange the configuration in the form of argon of, that is 3d8 of 4s2 of 4p0. This is what we are going to take. So therefore if you take 3d orbital, it has 5 orbitals, 1 2 3 4 5, 4s 1 and 4p, 3 vacant orbitals are there. So 1 2 3 4 5 6 7 8. So 2 unpaired electrons are there. Here we have 2 unpaired electrons. So this is 4s2, this is 4p0, this is 3d8. But because the carbonyl group is a strong field ligand, so it forcibly violates both these electrons, are forcibly sent into the 3d orbital. They are given the kind of demotion and forcibly they are brought to the lower set of orbital, that is 3d orbital. So therefore you are finding that now the new set of orbitals looks like this. Now it is going to be 1 2 3 4 5. So 1 2 3 4 5 6 7 8 9 10. So this is 3d10 and this is 4s 0, so vacant orbitals, and again this is 1 2, so this is 4p0. This is an exceptional case because actually we are expecting an inner orbital complex, but it cannot anymore utilize the 3d orbital vacant orbitals because all the electrons have been filled up in the n-1d orbital. So forcibly, though it is a strong field ligand, it is forcibly allowed to convert from the inner orbital complex to the outer orbital complex. So now exceptionally inner orbital converts to outer orbital complex. So temporarily it is showing the property of weak field ligand, but the ligand property is not changing. ligand is still a strong field ligand only, because there is no availability of the vacant orbitals in the n-1 d orbital. So forcibly it has to utilize the vacant orbitals which are present in the outer orbital complex. So therefore all the 4 carbonyl groups which are present in the complexes, they are going to utilize 4s orbital, 4px, 4py and 4pz. So therefore here this is going to become, instead of writing 4p0, I am going to write it as px, py and pz of 4p orbital. So therefore it is going to form sp3 hybridization. It is going to form sp3 hybridization. So therefore you find that hybridization is sp3, shape tetrahedral, shape is tetrahedral, number of unpaired electrons are 0. So therefore it is diamagnetic. So structure you can take nickel, carbonyl, carbonyl, carbonyl and carbonyl. This is metal carbonyl. So this is how it has the structure, and this is the complete information of the nickel tetracarbonyl. So here if you go to the next part of the complex, it's a cationic complex. So go for the, that is d bit, Ni, NH3 taken 6 times of 3 plus, write the nomenclature name of this. This is hexaamine nickel 3 complex, nickel 3 cationic complex, I can say. So what we are noticing here is, like, first of all let us make an analysis. Here the nickel oxidation number is +3. Here NH3 is a strong field ligand, so it forms inner orbital complex. If it is forming inner orbital complex, then it is utilizing n-1 of d, ns, np orbitals in the hybridization of the given metal complex. So now if you take the nickel here, nickel atomic number is 28, its oxidation state is +3. Okay, fine. If it is +3, orgon of, that is 4s2 of 3d8. If you take, then because it is carrying 3 units of positive charge, so I am going to remove 2 electrons from here, and I am going to remove 1 electron from 3d8. So this is going to become 3d7, because it is utilizing the n-1 of d, ns and np. Again I am going to rearrange the configuration as, that is 3d7 of 4s0 of 4p0. This also means that you go for 3d sublevel which contains 5 orbitals, 1 2 3 4. So 1 2 3 4 5 6 7 if you have, and here you have 4s orbital and you have 4p, 3 orbitals are there. So what we can do here is, like it has nickel atomic number is, yes, it is carrying +3 oxygen state. So we have removed 2 electrons from the 4s and 1 electron from 3d. So here we have 2 unpaired electrons are there in the d orbital, and we have 6 ammonia ligands, strong field ligands. So what is happening here is, like, it is going to pair up the 2 electrons. These 3 unpaired electrons are there. So this is 3d, I can say that this is 3d, this is 4s and this is 4p, where it has px, py and pz orbitals. So here what we are noticing here is, actually if you take ammonia is a strong field ligand, so it is going to forcibly pair up, this electron from the d sublevel. 1 electron is going to get forcibly paired up. So if it is getting paired up forcibly, then you are going to get the status like this: 1 2 3 4. So 1 2, so when it is coming over here, 1 2 3 4 5 6 and 1 unpaired electron is there. So this is the status of the 3d7 electrons after forcible pairing up, because it is violating the Hund's and Abbas principle, and you have the vacant orbitals here, 4s, and this is also 4p. But one thing what we have to understand here is, suppose if it is utilizing the 3d vacant orbital, it will utilize the 4s orbital. It is going to utilize the 4px, 4py and 4pz. Only 5 vacant orbitals are there, but the number of ligands inside are 6, and that means forcibly it is going to utilize even the vacant orbital of the 4d orbital also. So the metal in any complex, the metal cannot simultaneously utilize the inner orbital, the inner d orbital and the outer d orbital at a time. That is why it will ignore this vacant orbital. It will ignore this vacant orbital and it will stick to the same 2 unpaired electrons which are present in the 3d7, and it is going to, that is, I mean to say here I am going to use 1, 2, 3, 4, 5 vacant orbitals are there, 4d. So here I am going to take one more vacant orbital. So this combination will work out 1, 2, 3, 4, 5. This is going to work out. This is 4d. So it is not going to forcibly pair up these 2 unpaired electrons. And then the 6 ammonia molecules in the form of strong field ligands, they ensure that the 2 unpaired electrons are remaining as it is in the case of 3d orbital, and now it is going to utilize the 4s vacant orbital, 4px, 4py, 4pz, then 4dxy, 4dxy, 4dyz orbitals are going to be utilized. So therefore, surprisingly, the hybridization of the complex is going to become, that is, sp3d2 complex. Surprisingly, it is outer orbital complex. sp3d2 hybridization. Then you can see that surprisingly, that means it is playing a role of, though the ligand is a strong field ligand, it is playing the role of the weak field ligand. It has 2 unpaired electrons here. So the number of unpaired electrons are 2. So therefore the complex is going to become paramagnetic. However, the geometry is octahedral geometry. So you can just take the nickel like this and take the 4 complexes, and we have 6 ammonia molecules. So therefore take one ammonia, here you take one ammonia, here you take one ammonia, and ammonia. So this is going to become the octahedral complex. So this is the geometry of the hexamine nickel 3 cationic complex.